喂，有吗？好，再一次，喂，有吗？嘿，靠，没有声音哎，为什么？真的哦，那我换一支麦克风。好，我再一次，我换一支。喂，有吗？这个摊比例蛮大的哦。所以有哈。他说有，就好了。太慢了，但应该可以吧？这样有差吗？声音有差吗？我问一下这样。这样，他说我讲话大概过5秒后才会听到声音。没关系，反正，要把那个延迟开低啊，你把它延迟调低。叫他延迟调低一点，好。喂，你把延迟调低一点看看。那个可能要关掉重开，我就不用了。好，OK。好，那不然这样还要吗？他说这样要先关掉，这样等于要重用。不用，没差。大不了之后影片把它剪下来，然后不用，根本不用，根本不用。对吧？好，随便大概有声音就好。好，OK，算了，没关系，这样就好了。对啊，反正他们又不是追直播。对，应该也有可能会这样。好，没问题，没问题。好，拜拜。
All right. Good afternoon, everyone. This is control systems. For those of you who are in the wrong classroom, the exit is there. Are you aware that this is control systems, third year course in EE, electrical engineering? How many of you have not successfully enrolled yourselves in the course? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Why are there so many of you? Right. So this course is not going to accept any third-year students from the Chinese stream. If you yourself are one of those, you can leave now, and you're not going to be able to enroll in the course. For others, maybe, shall we do it now? Well, for those of you who like to enroll in the course but have not successfully done so, please bring out your forms to me right now for signature. It's not this week. So it can only be done next week. Wow. So the forms cannot be printed out in advance. Okay, fine. When next week? Well, better have a valid reason to enroll in the course, because we're not going to accept any Chinese stream students, as we said. Okay. So what else? So this, again, is control systems, and my name is Seijun Kong. So today's lecture, we're going to cover some practical information and ground rules for the course. We keep having students entering the classroom. Have we got enough seats for everybody? It just doesn't make sense. Why are there so many of you? And you're not supposed to be here. Why are you here? Look at the congestion that you've created. You appreciate it? All right. So I'm the instructor, Seijun Kong. I wouldn't say I'm someone new here. I may be someone new to this university, but I have done research and taught on 4 different continents, including Australia, Sweden, the US, and Hong Kong, before joining NSYSU as an associate professor. So we've got 4 teaching assistants for this course. They are Lin Yuren, Liao Yiquan, Chen Tingyue, and Wu Boyuan. And we'll have them introduce themselves to you. So these are the faces that you should remember. If you have any questions, bother them. Don't bother me. Just kidding.
I'm Lin Yuren, and if you have any question about the class, feel free to email to us. And this one is my email. And you can find me in the lab, EC 7022B.
Okay, I'm Chen Tingyue, and if you have any questions, please feel free to meet us at EC 8016-2.
My name is Liao Yiquan.
好，大家好，我是吴博元。我有问题可以找我们，然后传mail或是到实验室找我们都可以。对，希望是不要有问题。好，谢谢大家。希
望是不是我的课清楚到没有人有问题？对，没错，非常棒。All right, so let's proceed to the next slide. Students who have enrolled themselves in this course are assumed to have passed the following two courses, linear algebra and signals and systems. So some topics from the above courses may be very briefly reviewed in control systems. However, you're expected to master whatever they have been covered in these courses. It is your responsibilities to make sure that you are comfortable with the material covered in these prerequisites. And if you are not, it is again your responsibility to seek help from, for example, the TAs or your fellow students, okay, in understanding the course materials. Right. Some information about lectures, tutorials, and quizzes. So lectures will be held. You can't find a seat. Yeah, well, you can have a seat somewhere. Maybe, yeah, right next to the screen, if you like. Lectures, as you know, will be held every Friday from 1 o'clock to 4 o'clock in this classroom. Yeah, the two of you can share one seat. Yeah. There are other chairs available. There's just one more, I believe. Yeah, there's one seat over there. Is this taken? Yeah. Yeah. So one of you can sit here, if you like. Yeah. You just stand here. There's a weekly tutorial session that is scheduled right after the lecture. So the tutorial will be Q&A based, it's question and answer based. The session ends when there are no more questions, okay? There will be mandatory 15-minute quizzes given out every Friday at 1:10 p.m., except in weeks 1, 9, 14, and 16. So week 1 is today. Weeks 9, 14, and 16, you'll be having exams. So there will be no quizzes given in those weeks, on those Fridays of the week, but a quiz will be given out on in every other week on Friday, 1:10 p.m., even if it's a national holiday or a typhoon holiday, okay? So I believe in 2 of the weeks during the semester, there will be a national holiday that falls on Fridays. So the quizzes will still be given out on those days. But at the end of the semester, when we try to calculate your score, we may take a maximum out of 12 quizzes. So a maximum of maybe 10 out of 12 quizzes. So your best performance will be counted towards, why are you here? Why are you here? Why are you guys here? So I'm pretty sure you passed with A+ last year. Why are you still here? So again, in summary, quiz will be given out every week, except during the exam week, and only your best performances will be counted towards your assessment. Okay. So, for example, there are 2 holidays during the semester. Those quizzes, you are free to not take them, and you'll still be able to score full marks for the quizzes. But you're strongly encouraged to take those quizzes because only your best performance will be counted. Is that clear to everybody? Yeah? Any questions so far? No? 真的没问题吗? The more information will be provided to you regarding the quizzes later by the TAs. Course materials were placed on the NSYSU e-learning website. How many of you have seen the course, these lecture slides? uploaded to the course website, to the e-learning website, whatever it's called. How many of you have seen it? Or how many of you have downloaded it? Do you have access to the e-learning website? You do. But those of you who have not enrolled in the course do not have access to it, but for others you do, don't you? I don't see not, actually. Do you or do you not? And 很明显就有啊，你回答一下，你有不行吗？有，给你们气死。Textbooks and references. So our course will be based on the textbook by Franklin et al., titled Feedback Control of Dynamic Systems. There are some reference texts provided here on the slide. You are free to read them. Lecture notes are not replacement of the textbook, and you're strongly encouraged to study the textbook. We'll follow the textbook fairly closely, and you're again strongly advised to read it. So this slide is about the assessment. Very important information about this course. So there'll be one mid-semester exam not exceeding 3 hours that is worth 35% of the assessment. It will be held in week 9 on November the 7th. And there's one final exam not exceeding, again, 3 hours that is worth 35%, which will be held in week 16 on December the 26th. The in-class quizzes that I mentioned earlier are worth 30%. These are online quizzes that you will take using your pads or iPhones or Android phones or laptops. For example, at 1:10 p.m. every Friday, except on exam days. Okay. More information will be provided to you by the TAs later. There is one bonus exam, again not exceeding 3 hours, that will be held in week 14 on December the 12th. And this exam is worth, well, you don't have to take it. In order to score full marks, you don't have to take it. But if you do, for every point that you score, it will be counted towards your final assessment. So this is plus 10%. So you can see that the total adds up to 110%. So this is something that gives you 3 points. And you're again strongly encouraged to take the exam because you might find some of the exam questions rather familiar during the final exam. Did you get my hint? Yeah. At least 2 of you got my hint. So this exam here, this bonus exam here, that will be held in week 14 on December the 12th. You don't have to take it. Even if you don't take it, you will still be able to score 100% of the assessment. But you're strongly encouraged to do it because some of the questions will appear familiar to you during the final exam here. And this is worth plus 10% mark, so whatever that you get will be added towards your final count. Okay. Is that clear to everybody? 有问题就问，有问题吗？完全没问题。Go ahead. Yeah, you have not enrolled in this class. Yeah. Oh, so that's tricky. So when will you be able to enroll yourself successfully in the course? Next week? Which days next week? Okay. Let me ask the TAs. So we will prepare for you paper quizzes next week as well, for those of you who have not enrolled in the course. So you can take the paper quiz instead of the online quiz next Friday. So I answered that students' questions. Are there any other questions? Or did you not hear my answer? So for those of you who have not enrolled in the course, there will still be a quiz next week, but you take the paper quiz instead of the online quiz. Okay? Because you will not have access to the e-learning website yet next week because you are not enrolled in the course. Is that clear? Any other questions? No? So you can see on this assessment sheet that I won't be taking rows. So I won't be taking down your names. I'll pass around a sheet of paper for you to write down your names later, but that's not going to count towards your assessment. So for those of you who would like to leave now, please feel free, because your attendance will not count towards your assessment. Collaboration is strictly prohibited in examinations. Okay, I don't think that is something that I should let you know, because you should be well aware of this fact already. Are there other questions that you'd like to ask? No? Okay. So maybe I'll let the TAs to tell you more about the quizzes then.
Maybe some of you have noticed there's a demo quiz on e-learning website, and it's a demo quiz, so it's not the formal weekly quizzes, and you can do it now because it is used to familiarize you with this e-learning website. So you can do the quiz, and if you encounter any problem, you can raise your hand.那个网络大学上面的系统有小考啊，然后这个是一个 demo， 就是它不是正式的考试，那只是给你们测试一下，说就是之后如果用网大小考的话，会不会遇到什么问题？所以你们现在如果手边有手机或者是平板之类的，可以现在拿起来，就是直接练习一下啊。如果有什么遇到什么问题的话，可以举手跟我们说。然后这边提醒一下同学，就是每一周的考试是除了当周有那个 exam 之外，基本上每一周都会有小考。就是如果今天是因为假日放假的话，或者是台风的关系没有上课，那一周一样会有小考，就是大家不要忘记。好，然后那我。然后还有一件事情要同学注意，就是基本上小考都不会有任何的补考，就是如果你们今天是因为个人的因素的关系，就是可能没有考到试，那基本上就没有办法进行补考，就是除非今天是这个网络大学的系统有问题，不然的话我们的小考一律都不会补考。那有人做这个测验有遇到什么问题了吗？
So again, let me remind you that the quizzes will still be given out, will still be held on days that are national holidays, okay? On days that are typhoon holidays, okay? So you are free to not take those quizzes that fall on holidays, and you'll still be able to get full marks for the course. But then you're strongly encouraged to take them because we will, at the end of the semester, take your best performance and count them towards your assessment, okay? Is that clear to everybody? Please please sign on a sheet of form and pass it around. It won't be counted towards your assessment. 应该不会，我很懒。这是谁的？ All right, let's continue. I believe some of you have been exposed to control before. Right? For example, you may have taken a similar course last year, or you may have seen control in one of the other courses or subjects that you have taken during a second or third year. So you should be well aware of the fact that control is mathematics oriented. Okay? Understanding the concepts and the big picture is way more important than memorizing formulas. In this course, I cannot stress the importance of this item enough. So let me give you an advance warning. Memorization without understanding the concepts or the big picture will lead to poor exam performance and a significantly higher probability of failing the course. Yeah. So I hope you will be able to understand the course materials instead of just memorizing whatever formulas that underpinned the course lecture slides. Our exam will focus on understanding, not your ability to blindly apply formulas. So these are exams that are unlike those that you have taken probably during high school years or the first or your second year subjects. So you're strongly encouraged to study consistently, persistently, and constantly. Learning does not happen overnight or within a day, right before the exam. Okay. So here are some of the course contents that we will cover in this course. Probably not all of them, but let me just list out some of them on this slide. So from weeks 1 to 8, we will be exposed to feedback. We'll see a motivating example. We define our control problem. We will perform modeling and see what modeling errors are. And then we'll learn about linearization. We'll do a review of continuous time signals and systems. Then we'll talk about open loop control, closed loop control, stability and Routh's algorithm for verifying stability, as well as root locus methods. And starting from week 9 up to the end of the semester, we will cover Nyquist analysis, relative stability and robust stability, and other topics such as sensitivity analysis, simple proportional control, which we will see already in this lecture later, and then lead lag compensator design, PID control method, which you may have seen in other courses, pole placement method if we have time, and architectural issues in single input, single output control systems, CISO systems, and as well as dealing with constraints imposed by the physical nature of systems, if we have enough time to cover these topics. Okay? So roughly speaking, we're going to cover chapters 1 to 6 of our textbook, Feedback Control of Dynamic Systems. Any questions so far? Nope. Okay. So let's now begin with an introduction to control. So this part of the course is going to be based on a motivating example. In this lecture, we'll introduce some key concepts of control system design using an industrial example. This example will demonstrate a few concepts, including the effects of feedback on measurement disturbances and dynamic response, the use of feed-forward to reduce input disturbances, and finally, trade-offs in the use of feedback. All right, so here is our industrial example. Our problem is to consider the control of the level of a material in a mold. There's another seat here, if you like. Yeah.不用那么礼让了，坐就坐了。So this is going to be our mode, and our control objective is to control the level of whatever liquid that's contained in this mode here. So there will be input from the ton dish of the liquid, and there will be outflow from the end of this cast here. So our goal is to control the level of material or liquid in this mode. So what are some key performance goals that we can set for the problem? What do you think are some of the performance goals that we can set for this problem? Any ideas? Sure, you can read them off from the slide, but I'd like you to think about this as a real control problem. So you've got a container or whatever, a mode or cast strip, as in the title of this slide, and you'd like to control the level, the height of the liquid or material in the mode. So what are some control goals, control objectives that you can set for this problem? Of course, one of them is safety. It's got to do with safety issues. The level of the mode the level of liquid should never be in danger of overflowing or emptying, as either case will result in matter spilling with disastrous consequences. So you would not like to fill up your cast with so much mold that it overflows, or you will not like to close this valve and stop the input flow such that the output flow will dry out the entire cast strip. So you basically what this means is you do not want this to overflow and you do not want this to be empty. Okay. And also there might be profitability issues that you take into consideration in your design of controllers. That might include product quality, maintenance, and overall throughput. So on the next slide, we will take our first step of developing a simple schematic showing the important aspects of this process that we're trying to model and then control. Okay. So this is a motivating example. It's an industrial example, a practical example to motivate for you the benefits of performing control or learning control theory in this course. Okay. So as we have seen before, basically what we have here is some sort of container that contains the mode. There will be input flow rate controlled by this valve, and then there will be outflow of the mode at the end of this container. So our control input is then Qi here, which we can do by turning on and turning off the valve. And this height here, H, is the level of the liquid or material that we're trying to control. So we will not like it to go too high in such a way that the liquid overflows, or we will not like this to go too low in such a way that the tank empties out. So that's just one of our control objectives. So in order to control this object here, what do you think we should do? Well, one way to do it is we could personally go there and turn off or turn on the valve ourselves and keep staying there and observing the liquid with our eyes. So that is a manual control that we perform. Maybe human in the loop, that works, provided that you can stay there forever. Okay. So what if you like to automate this process? How are you going to proceed with controlling the level of liquid or material in this container? Well, you need to understand the dynamics of the process to begin with. You need to have an understanding of how the inflow and the outflow affect the level of the material in this car strip, at the very least, in order to control it. Does it make sense? No. Now, how would you how would you go about understanding the process? Well, it's through the use of a mathematical model. So you like to mathematically model the dynamics of the material level in the container, the car strip, using mathematical equations, right? So the mole level is related to the inflow rate Qi and the outflow rate Qo by this equation here. So what does this say here? The height of the material is equal to some constant times the integral from minus infinity to the current time t, Qi minus Qo. And you integrate this with respect to the dummy variable tau. So the constant here is the reciprocal of the cross-sectional area of the mold. Okay? So what does this say? Why is the height of the liquid or the level of the material related to the inflow rate and outflow rate in this way? Can anybody answer the question? There are more than 80 of you in the class. I believe some of you will have answer to that question. Here. So you've got a container, you've got some liquid flowing in, and you've got the same liquid flowing out. At the inflow rate is Qi, the outflow rate is Qo. And this is the unit for Qi and Qos are volume per second, right? Or meter square per second, meter cube per second, for volume per second, or liters per second, meter cubes per second, cm cube per second. And how are you going to translate this into the level of the liquid in this container? Now I'm claiming that the height of the liquid can be expressed in terms of the product of this constant, which is 1 over A, where A is the cross-sectional area of the car street, the container, times this integral here, where the integrand are Qi minus Qo, so the inflow rate minus outflow rate. And I'm asking you why this equation holds. Why do you think it holds? You assume that you started from a long time ago, which is minus infinity. So that's your start time. So you started from minus infinity. That's your time. Okay. And you integrate from minus infinity until the current time t. So the height of the liquid at the current time t is given by this expression here. I'm just asking why. Why do you think this is valid? Why do you think this is a valid description of the level of the liquid in the mold, in the container? Anyone? No one at all? You're in year 3, right? Some of you are in your year 4. Right? So some of you graduate within a year. So.福林哥哥帮我一下。你们来干嘛？ All right. So as I was telling you, the unit of the inflow rate is what? Is volume per second, right? So you take the difference between the inflow rate and the outflow rate. That is the net rate of change in terms of volume in the liquid in the container, right? The difference between the inflow rate and the outflow rate will give you the net rate. Okay? The rate of change is volume per second. So then you integrate it, you integrate out the time. So you start from minus infinity and you integrate from minus infinity to the current time. So you take out the time. You're just left with whatever volume that is left in the container. Right? So volume per second times second, you get volume. So you get meters squared or liters. And then you divide it by the cross-sectional area of the mold. You get a one-dimensional information, which is the height. So area, the unit of the area is meter square. So meter cube divided by meter square, you get meters. So you just get one dimensional information, which is the height of the liquid in the container. Does it make sense? No? Any questions? Yeah. Okay. You're not making it any easier for me. All right. So this equation here can be expressed in a block diagram as follows. So you're going to be seeing a lot of block diagrams in this course. And this is just a schematic for you to get a feeling of how the signals are flowing, what information are being collected, what signals are being summed up or subtracted from each other, and what signals are being processed in order to produce another signal. So these are just block diagrams, so do not be intimidated by block diagrams in this course. You'll be seeing a lot of them in this course. Okay? So let's take a look at how this block diagram models the same equation up here. So what is this saying? This is saying that if you subtract QO from QI, so this signal here is QI minus QO, and then you integrate it, and then you multiply it by 1 over A, you get the signal H, which is precisely this equation up here. Okay? So here you can view this square block as a system that processes this input signal, which is QI minus QO. And it outputs, this system here outputs a signal called H. So this is a system, this is just a summation of two signals with a minus sign right in front of QO. And this is a system that takes in an input and gives out an output. Here in this block diagram, the outflow QO appears as an input disturbance. So this, you can view this as an input to the system, and QO as a disturbance that disturbs this input signal. Okay. That's just a viewpoint. So you can view QO as an input disturbance. Any questions on how this block diagram models the equation up there? Do you see that these two are just telling you the same information about how H is related to QI and QO? This is just a block diagram way of modeling the same equation up here. Okay? So one is just more mathematical, and the other one is just more, I don't know, artistic or diagrammatic. But they are the same thing. They're two sides to the same coin, okay? They tell you the same information. They're worth the same value. Okay? Any questions so far? So if you have any questions regarding block diagrams, you better ask them now, because you'll be seeing a lot of block diagrams in this course. And I'm sure a lot of you will encounter problems, especially during the exams, with block diagrams. So if you have questions about them, please ask them earlier than later. Okay, so here's another block diagram. So on this slide, we'll see the first use of feedback in this course. Feedback is 回收. Okay? So feedback system is 回收系统. Okay? feedback is one of the most important concepts in control systems. So you'll be seeing a lot of feedback theory in this course throughout the semester. So here is just to give you a feel of how feedback can be used to control the level of some material in a car strip. Now, let's take a 10-minute break. 欢迎大家回来。我想统计一下，想要加签的是有多少位？能举手吗？2、4、6、8、10、12、14。好。诶，超过课室容量，可以请4位不加吗？好了，我再想想怎么处理你们啊。那另外一件事就是，all right. So there were some questions regarding the quizzes. So let me give you a hint. So last semester, there were actually a lot of students who were able to pass the course without having passed either of the mid-semester exam or the final exam. So that's just to show you how important these quizzes are. Okay, so you really strongly advise to take them. So again, the quizzes will be held every Friday except in these weeks, except in week 9.你们想要加签的来找这位帅哥，现在来找这位帅哥，这出来，给这位帅哥认一下你们的样貌行吗？对，扫一下 Face ID， 没错。还是现在找一张纸，对，你们有纸吗？哦，有，对，用手机。 那我们加签就加这几位而已哦，最后啊，就别的就没了。那哎，我们最后决定。
同学那个要加签的注意一下，就是下礼拜一你们记得拿你们的加签单，然后到那个7022B 找我，然后中午12点到下午5点都可以过来，啊记得都礼拜一哦。
错过就没有了，啊。好，谢谢两位。All right. So, where were we? So I was talking about the significance of in-class quizzes. So you really strongly advise to take the quizzes which will be held every week, except during the exam weeks. Okay. Any questions regarding the quizzes? So I can't overemphasize the importance of these quizzes. Okay? Some of you may only pass the exam, pass this course because of the quizzes at the end of the semester. All right, so let's get back to our control problem. So it is desired for us to keep the mode level at a specified level R. Which is short for reference. So for this reference signal, which is given to us, we like the output, which is the liquid level, to follow the reference as closely as possible. Now, how are we going to achieve that? We're going to achieve that by using a feedback controller on this slide. So we're going to use a specific type of feedback controller called proportional gain controller, which is just multiplication by a constant k. So this k here is a proportional controller. So its output is simply proportional to its input. So output is simply a constant times its input. So this is a proportional controller. And here we'll be using the feedback mechanism, which is what? Okay? So this is our plant, the process to be controlled. Remember? So this is the inflow rate, the outflow rate, and the liquid level, height. So this is the plant that we're trying to control. So we're going to treat this as an input disturbance. This is our control variable. So this is something that we have control over. And how are we going to control the inflow rate? Is by turning on and off the valve. Remember? From the previous slide. So by opening and closing the valve, we can control the inflow rate of this mode into the container. Okay? So QI is something we have control over, something that we can control, something that we can change, we can modify. And the height or the liquid level is something that we like to keep. We like to keep at a certain level. Okay? So by controlling QI, we like H to follow a reference R as closely as possible. Okay? And we're going to achieve that by using a feedback mechanism. So again, this is the plant that we're trying to control, the process that we're trying to control, with input QI and output H. Okay? So this H here, we're going to use measurement of or observation about the liquid height, and then we're going to feed this signal back to here, and we subtract it from the reference. So this is called the negative feedback control. So the output of the plant that we're trying to control is fed back to before the controller. And then we subtract this signal from the reference here. So this is a negative feedback control mechanism that we are seeing on this slide. We'll be seeing a lot of feedback control later on these slides, but this is just for you to gain your first exposure to feedback control theory. Okay. What is DM here? DM here is simply a measurement disturbance. So this signal here denotes the measurement of the liquid level or the material height in the container. And because we're using a sensor to measure the liquid level, there will be some measurement disturbance that we model using this additive disturbance here denoted by DM. So DM is added to this measured signal H that is fed back to right before the controller. So DM can of course be a negative number, can be a positive number, it can be a signal that varies over time. So it's simply used to denote measurement disturbance. Okay? So as I said before, this feedback mechanism or paradigm is known as a proportional feedback controller because the control action is proportional to the error signal. So the error signal is simply this guy here. E, the error signal is the difference between the reference and the output of the plant H. Okay? So this is the error signal. And the control variable, the control action, QI, something that we have control over, is proportional to the error signal. So QI is simply a constant K times the error signal. So that's a proportional controller. Does that make sense to you? Yeah. So I'm just reading off the block diagram on the slide, right? So you can see that I'm pretty good at reading a block diagram. I hope you will be able to gain the same ability to do so. But right now, there's a steep learning curve for you. Okay? The block diagram is just a schematic. It's a CE tool for you to quickly grasp the essence of the signal flows as well as the presence of the systems that process the signals, etc., etc. Okay? So instead of writing all this down in mathematical terms, which are not very intuitive, this is simply a schematic for you to quickly grasp an understanding of how things are being controlled, what blocks are the plant, and what block denotes the controller, and how the signals are flown from which direction to what, from where to, from point A to point B, etc., etc. Okay? The signal flow directions are all reflected very clearly in this block diagram. Any questions? Yeah. All right. So suppose now this is the proportional feedback control that we're going to use to control our liquid level, the height, H. So now we've designed our controller, our feedback mechanism. So what's our next step? We're going to test the performance of our controller. Okay? So you've designed something. You like to see that it works. How are you going to see that it works? Well, you're going to run some tests. Okay. So the performance of a system can usually be tested using what's known as the step response. So the step response is a common way of assessing the dynamic behavior of a system. As the name would suggest, this involves examining the system output for a step function input. So remember what the step function is from signals and systems that you took 1 year earlier? So it's just a step function. Well, you see what the step function soon. Basically, it's just a function that looks like this. A 0 before sometimes, and then it increases to a constant at a time instance. So it's just a step function. Okay. It's just one step. It takes one step. It's just a function that is a constant before some time and another constant after some time. Okay. Now in this case, when the reference is a step function, what do you expect the output of the plant to behave like? So you would like the output to follow the step function, the reference, as closely as possible. So for example, this is our reference command. Our reference command is the liquid level might be 10 centimeters before time 0, and after time 0, we like it to increase to 20 centimeters, for example. Okay. So under this reference command, we would like the output, which is the actual liquid level in the container, to track this reference input as closely as possible. So it should be 10 centimeters before time 0 and 20 centimeters after time 0. But obviously, such a physical process cannot make an instantaneous jump, unlike the reference signal, which is just a function over time that we have full control over. This physical process will have some time to adapt to the reference input, assuming that this feedback control mechanism works as we desire. So the output of the plant, which is the liquid height level in our case, should converge to the reference as quickly as possible and with as little deviation as possible. So that is something that we strongly desire of our feedback control system. Does that make sense? So we like the output of the plant to follow the reference input as closely as possible. So in our simulation, so we're going to simulate our system's response to the step reference input. And the system that we're simulating is the feedback control system that we have shown on the previous slide. So in our simulation, we're going to set the reference to be a unit step function, which means it's 0 before time 0 and it's 1 after time 0. We're going to set the outflow rate, which we treat as an input disturbance, as 0.5 times 0.1 times sine pi t. Well, it can be any function, but we're just setting it to be this function to observe its effect on our feedback system. And then we're going to set the measurement disturbance as this function here, which is 0.1 times sine 2 pi t plus 0.05 times sine 3.6 pi t. It's just some signal that we use to simulate a measurement disturbance to our feedback control system. And then we're going to observe their effects on the feedback control system that we just designed. So the plots here show the system response and the resulting control input for k equals 1 in blue and k equals 5 in green. So at the bottom here, at the bottom plots, these are the control action, meaning the valve actions. So the inflow rate. So this is Qi, and this is H, the green and the blue. And the red here is the step reference. Okay? The step reference input, the step function, 0 before time 0, and then it increases to 1 at time 0, at the time instant 0. And for the blue curve, that is our H when k equals to 1. And for the green curve, that is H when k equals to 5. Okay. Similarly, here, the blue curve is Qi when k equals to 1. And the green curve denotes Qi when k equals to 5. Okay. So do these plots make sense to you? Yeah, these are just simulation plots based on what we have here. Okay. So the reference, again, the R is the unit step function. QO, the input disturbance or the output flow rate, is this function here, and the measurement disturbance, DM, is this function over here. And these are the actual plots, the simulation plots that we can obtain from our feedback, from simulating our feedback system against the list of functions shown on the previous slide. Are there any questions? Is there any bit that is unclear about this slide? So immediately, what can you observe from the results of these simulations? Are there any observations that you can make regarding these two plots here? Anyone? No? Are you following the course? Are you following the lecture at all? Or you're lost in translation? Or your mind is simply blanked out? You're thinking about dinner later? Feeling hungry? Any questions so far? Or any observations they can make of these plots? So why does the output look like this when k is set to 1? Or what is k? Can anybody tell me what k is? Does anybody remember what k is? What is k? What does k equals to 1 mean? What does k equal to 5 mean? Go ahead, please. Proportional controller, exactly. So that is the gain of a controller. So remember what k is? K is simply the gain of a controller. So when we set k equals to 1, that means Qi is equal to E, which is equal to R minus H directly. When we set k equals to 5, that means Qi is equal to 5 times E. And E is R minus H. Well, R minus H minus dm, okay? So that's our proportional gain controller, the gain of a controller, k. Okay. Very good, thank you. At least someone responded, finally. Or you can respond in Chinese as well if you prefer. But please give me some response. So I myself need some feedback as well. So this is a course about feedback. So I, as an instructor, would desire some feedback from you. Otherwise, I'll just be doing open loop control all by myself. All by myself, don't wanna be. So when k is set to 1, our output plan looks like this. And when k is set to 5, the liquid level looks like this. Well, you can immediately tell that there's huge difference in performance between these two signals, right? So the value of our proportional gain controller affects the control system performance significantly. Okay. So when k is set to 1, well, here we can make several observations. The output of the plan does not reach the new set point, which is 1, ever. But the deviation from the set point decreases as k increases. So what does that mean? So sorry, this should be capital K instead. Okay. So what does that mean? So the deviation from the set point decreases as k increases. Okay. So when k is set to 1, there's a huge gap between the new set point 1 and the output of the plant, the liquid level, the mole level. But when k is increased to 5, the gap decreases significantly. So the liquid level approaches the set point better than for the case k equals to 5 relative to k equals to 1. So immediately you can see from this plot that the value of k, which is our controller, affects the control performance very significantly. So that is the first point. We can see that the output does not reach the new set point, and also the deviation from the set point decreases as k increases. Okay. Additionally, there are short-term oscillations due to the measurement disturbance. And this oscillations, the magnitude of the oscillations increases as k increases. So what does that mean? So you can see that there's oscillation here, and there's also oscillation here. And these are due to what? The measurement disturbance. Okay. The measurement disturbance is what here? Again, this function here, which appears in the block diagram over here. So this measurement disturbance is something that we use to model, for example, the inaccuracy of our sensor that we use to measure the liquid level. Okay? So this liquid level here, well, we have to observe it. We have to measure it using some sensor. Well, we could observe it with our eyes, but then our eyes are sensors themselves, right? So there's bound to be some error in our observation. So we can't precisely measure what the liquid level is. So there's always some measurement disturbance, measurement error in our measurements. And dm is the signal that we use to represent or model that disturbance. Okay. So this is modeled as an additive measurement disturbance to our actual measure signal. Okay. So we can see from the plots that the measurement disturbance indeed affects our control performance. And in what ways? Because our measurement disturbance was chosen to be a sinusoid of this form, or sum of two sinusoids of this form, so they are periodic sinusoidal waves. that translates into oscillations in the liquid level or the mole level in our control system. And one more observation that we can make is that as we increase K, the oscillations increase in magnitude. Can you see that? So when K is equal to 1, the oscillation has a smaller magnitude relative to the case where K equals to 5, where you can see the oscillations increase in magnitude. Okay, so this are some of the observations that we can make of the plots of the control performance of our control feedback system. Well, these observations clearly demonstrate that our current design is inadequate. The deviation from the set point can be attributed to the input disturbance QO, and we can fix that using feed-forward a mechanism which is used to remove this disturbance. More about that later. So based on these two based on these two observations, we can see that the value of, so how well our controller is designed clearly affects the control performance of our feedback system. Okay. So we can see that as K increases, the deviation from the set point decreases, but the effect of the measurement disturbance also increases, which appears as oscillations in our output plant, in the output of a plant. Does it make sense? As K increases from 1 to 5, our liquid level gets closer to the reference input, which is 1, but the oscillations caused by the measurement disturbance also increase in magnitude. Okay. So, well, more details about that. So right now, we're going to try to take care of the problem with the deviation from the set point by using a feed-forward mechanism. So how are we going to remove the effect of the input disturbance, QO, yeah, the outflow, the liquid outflow? Well, assuming that we can measure QO, then we can feed it forward to the reference. So here, feed forward involves removing the input disturbance at the controller input. For this example, we assume that we can measure the casting speed, which is the outflow rate of the mole. So by having access to QO, we can then feed it forward to here after multiplying it by 1 over K, and then add it to the difference between R and H. So what does this part do? Can anybody tell me what this part does? So this is the only difference from the previous picture, previous block diagram. So this bit here with the block and this signal here, this is the only difference from the previous block diagram. So can anybody tell me what this is going to achieve? But here, in my feed-forward design, I have used 1 over K as a multiplication gain, as a gain. So 1 over K appear as if it's not there at all. So here, so what's going to happen is, without this part, you will always have minus QO in this signal. But once you have fed this forward, so this is 1 over K times QO. That's added to this signal. You add 1 over K times QO to this signal, and then you multiply it by K. Here, that means you're adding QO to this signal. So you're adding QO to this signal, and then subtracting QO from this signal. That means QO has just vanished. It will appear as if it's not there at all. Does it make sense? Forgot to use the mic. Okay. Let me explain again. So without this part, as I was saying, we go back to here. So QO will always appear as minus QO in this signal, right? Because this is QI minus QO. So minus QO will always appear here without that part, the feed-forward block. Okay? Now I've added the feed-forward block to this diagram. Now in this new block diagram, I have QO here, QO minus QO here, QO multiplied by 1 over K appearing here, and then this is added to this signal. Everything is linear, so K multiplied by R minus Y plus 1 over K QO will be my new QI. Right. I should write it down maybe. New error signal now. So my old error signal used to be just R minus DM minus H. So my new error signal now is R minus DM minus H plus 1 over K QO. So E is here, okay? This is E. Can everybody see why? E is equal to R minus DM minus H plus 1 over K plus times QO, okay? Just read it off the block diagram over there. Okay. So then QI is equal to K times E, which is then KR minus KDM minus KH plus QO. Make sense? Multiplication operation is a linear operation. I believe you learned about linearity in signals and systems or linear algebra. Okay. Somewhere you must have learned it. Okay. Okay, so QI is equal to that. Now let's call this U. This signal here U. I don't want to write it here because I can rub it off. Okay. So U is then QI minus QO, which is then this. So does QO appear in U anymore once I've performed feed forward? It doesn't. And can you see why? Well, it's why. Mathematically, you can see why. You can also see from the block diagram that QO has vanished from the signal U. Any questions? Yes? So QO is always present in our system. So QO is the outflow rate of our mode, the casting speed. Yeah. Because it's always there. We can't take it out. It's always there. It's not something we have control over. We have control over QI, but QO is something there, yeah. So this is used, the mode is used to cast something later. So this is always there. We can't, well, taking it out means shutting this off, and that means throwing away this entire, yeah. It's not a control variable. We have no control over it. Yeah. We have control over QI, but not QO. Yeah. So great question. So why do we need QO here? Because it's part of the model. It's part of the plan. So remember what our plan is. So our plan is this. So it consists of everything here, QI that we have control over, we can set it to 0, so this guy can disappear. But QO will always be there. It's not something that we have control over. And then this block here, which is 1 over A times the integral, that's going to be there in order to translate flow rate to our liquid level. Okay? So these are not something that we can simply change by, well, of course we can change this to 0, but then that's not feasible, because that's not our application anymore. This is meant to model a real physical system expressed mathematically up here. Yeah. Any other question? Yeah. Sorry? The same measure to DM. Not really, because here DM is not something that we can measure. So DM is measurement disturbance. So if you like to apply the same method to DM, that means you can measure the measurement disturbance. So which is not. But great question, very good question. Yeah. So it's not physically realizable to be able to measure the measurement disturbance. So if you measure this, I believe there will be more measurement disturbance that you introduce to the system. So you're trying to measure the measurement disturbance. Yeah. Great question. Thank you. So here, in order to apply this feed-forward mechanism, we have assumed that we can measure the outflow rate, which is something sensible. Of course, you're going to ask, why doesn't this measurement introduce measurement disturbance? Well, we're assuming that you don't, but even if you do, then this feed-forward mechanism means that you will not be able to fully cancel out QO in signal U. Okay? If measurement disturbance is present in the measurement of QO, then you will not be able to fully cancel out QO in U, which is still acceptable. Yeah? All right, let's take a 10-minute break and we'll be back. All right, let's try to get through the last few slides. Now we're going to simulate the response of our control systems with feed-forward. Okay, so suppose now we've designed this feed-forward mechanism together with our feedback mechanism. So we have appended the feed-forward design to our feedback control system. And then we're going to do the same simulation as we did before. So remember, we ran some simulations on this slide, and we have observed that for different values of K, the output of the liquid level, the mode level looked like this, and the control action looked like this. So now we're going to do the same for this feedback control system appended with a feed-forward mechanism. So here, again, we're going to run our simulations against the list of signals written on this slide. R is a unit step function, QO is a sinusoidal, is translated from 0 to 0.5, and then DM is a sum of two sinusoidal waves. Okay. And here are the results. For K equals to 1, our liquid level looks like this in blue. So H in blue for K equals to 1 is this curve, and H for K equals to 5 is the green curve. Okay. And similarly for control action, K equals to 1 gives out the blue curve. So this is our QI. Whereas for K equals to 5, the green curve shows us the signal QI over time. So what observations can you make of these plots? So can you make some observations from this plot relative to what you have seen 2 slides earlier? So just compare this against this with the feed-forward mechanism appended to our feedback control system. So what's the difference? Anyone? If you're following the lecture, I believe you will be able to spot the difference. So what have we done with the feed-forward design at all? Anyone? No. Exactly. So the set point is 1. Thank you. Very well. The set point is 1, which is a step response. Which is a step function. So here, our feed-forward mechanism has removed the effect of input disturbance from our feedback system. So now the output of the plant, which is H, actually approaches the set point as time progresses. So you can see that the deviation from the set point is a lot smaller compared to 3 slides earlier when we do not have the feed-forward design. So here you can see that the gap persists, the gap between the output liquid level, and the reference persists throughout the time. And also for both K equals to 1 and K equals to 5. Whereas after removing the effect of the input disturbance using our feed-forward control, you can see that the deviation from the set point is a lot smaller. That means the effect of the input disturbance has been removed from our feedback control systems using a feed-forward mechanism. Make sense? Any questions? Yeah. All right. But one thing remains, one thing persists here, which is what? The oscillations. The oscillations have not been removed because we have not dealt with the measurement disturbance. So we can see from this simulation that for a smaller value of k, your response speed is slower. So the output liquid level follows the reference input at a slower pace for smaller values of k. Whereas for larger values of k, your response speed is going to be faster, but at the same time, the effect of your measurement disturbance will also be larger. Okay? That means your oscillations caused by the measurement disturbance will be more visible in your liquid level measurement. Does it make sense? No? Yeah. So we can make the following observations as I've just mentioned. It is clear that feed-forward has removed the effects of the input disturbance so that the deviation from the set point is now close to 0 compared to the case where we did not have feed-forward design. So that's the first observation that we can make. The second observation that we can make is that the rate of convergence to the set point by h is faster for larger values of k, right? So that's the second observation that we can make. So as we increase k from 1 to 5, the response becomes faster. Yeah. The output liquid level h approaches the set point faster when k increases. Right? But using a smaller value of k reduces the effect of measurement disturbances. So a smaller value of k results in less oscillations in the output liquid level. Yeah. Yeah. We measure what we have full access to set point. R is what we design. R is what we set. Reference. This is what we desire. Yep. Yes. Exactly. We didn't take care of the measurement disturbance at all with the feed-forward. So the feed-forward design is just to remove the effect of the input disturbance QO from our feedback control system. And that results in a closer, nothing about the oscillations. Exactly. Very well. So we haven't dealt with the measurement disturbance at all. And the measurement disturbance causes the oscillations in the output liquid level. So the oscillations persist, and the effect, the magnitude of the oscillations increase as k increases. Okay. And k is our gain of the controller. So by having a larger oscillations in the output, that's going to increase the wear on the actuator. Okay? Large oscillations are undesirable. Okay? Oscillations cause wear and tear on our actuators. So what does that mean? That means there's a trade-off between the speed of response and sensitivity to measurement disturbances. So remember, a larger value of k gives us a faster response, but also a higher sensitivity to measurement disturbance. So a faster response means the output of the plant approaches the reference input faster. A higher sensitivity to measurement disturbances in this example means that the magnitude of the oscillations increase. Well, in general, it means that the effect of the measurement disturbance will be more visible in our control system. Okay. So that means there's a trade-off. There's a balance between the speed of response and sensitivity to measurement disturbances. We need to strike a balance between these two. So if we'd like to have a super fast response, we can set k to equal to 100, for example. Then maybe this plot will go almost instantaneously to 1, but then you have huge oscillations throughout, which is totally undesirable. Or you can set k to be equal to 0.1, then the speed of the response will be very slow. It might take several minutes for the output level, liquid level, to reach 1, but once it's reached 1, there's not much oscillation that you can observe from it. So there's always a trade-off. You can't have the cake and eat it too. You can't have everything you desire in the world. Okay? In control systems as well. Trade-offs of this type exist prevalently. They are ubiquitous in control systems. So trade-offs such as that seen in this example are a very common part of control system design. Well, even though a more sophisticated controller that we'll learn later in this course, for example, PID controller, PDP, or other types of lead lag compensators, they can give us a better trade-off, but fundamental limitations on control performance remain. One aim that we have in studying control systems is to know what can be done and how to do it. Okay? So our exploration of control systems in this course can be roughly split into two parts. First is analysis, and the second is synthesis or control system design. So analysis means given a system or open loop system or closed loop system, we like to analyze its characteristics. We like to analyze its stability, its robustness, its sensitivity to measurement disturbances, to input disturbances, etc., etc. That's what analysis is all about. And then there's synthesis or control design or design. That's about developing a control algorithm or controller for a given plant. Plant means a system to be controlled, a process to be controlled, to meet a set of specifications or a set of control objectives. So that's the system design, the control design part of the course. So this course is roughly split into two parts. It's analysis and synthesis. So analysis means analyzing the properties or characteristics of a system. Can be closed loop, open loop, etc. Synthesis means designing a controller for a given plant to meet a set of specifications or control objectives or goals. Okay. So are there any questions so far? No? Really? No questions at all? Okay. If that's the case, then yeah, we can wrap up today's lecture and off you go. See you next week.